In a recent section, we looked at things like this, and we showed that these do form vector spaces. But notice here, this has one, two, three, uh, four components, four coordinates, and so therefore this forms a vector space that's a subspace of R4. So what I want to do is show how to find the basis of that vector space. So here's what you do: you take the regular form here, a b 0, a plus b, and then we're going to factor this or deconstruct it into a times something plus b times something. Now the something we put over here is going to be the coefficients from a and b in this. So over here we'll get for a we've got 1, 0, 0, 1. And then for b we've got 0, 1, 0, 1. And these two vectors here, these form a spanning set of the subspace of vectors with this form. So it's a spanning set. All we need to do now is ensure that it's linearly independent. And in this case it is, because in this case it's easy because we've only got two vectors. And if you have two vectors, either they're multiples of each other or they're linearly independent. And these are not multiples. So what we can say is these are linearly independent. And therefore form a basis of the subspace. All right, let's look at this next example. This next example says find a basis of the subspace of R4 consisting of vectors of this form. And this is really long. So I'm gonna do the same thing here. We've got A, B, and C here. So this is going to be A times something plus B times something plus C times something. And we're going to go through and pull out all those coefficients, and that's going to give us a spanning set. So let's see for A. I'm going to actually write this above here. A, we've got 1 in here, 3, 4, and 0. All right, the coefficient of B is 4, -1, 3, 13. Four, -1, 3, 13. And for C, let's see, C we've got 1, 0, 1, although we got cut off, and 3. All right, so those three vectors form a spanning set. Are they linearly independent? Well, I can't just look at them and tell. Sometimes linear combinations are easy to see, sometimes they're not. So here's what we're going to do. We're going to take these like this: 1, 3, 4, 0, 4, -1, 3, 13, 1, 0, 1, 3. We're going to take these and we're going to row reduce this. And row reducing is going to kind of sift out all of any linear combinations that happen to be in there among them. So I'm going to put that in as my matrix. Let's see, 1, 4, 1, 0, 3, -1, 0, 0, 4, 3, 1, 0, 0, 13, 3, 0. All right, now I'm going to row reduce this. And notice we get this right here. We get a free variable over here in the C column. Now, I do want to copy this onto my paper. Let's make it fractions so it's easier to see. So we get, let's see, 1, 0, 1/13, 0, then 0, 1, 3/13, 0, and then 2 rows of nothing but zeros. All right, let's hide that. Okay, here's the deal. This vector and this vector are linearly independent from each other. This one over here, because it's a free variable, that tells us that this third, that tells us that C is a linear combination of A and B. So what we can do is we can throw out the vector that goes with C. Now, don't grab these vectors. That's not right. Come back over here, and these two are the ones we want, the ones that correspond to the leading ones. So the basis that we have here is going to be 1, 3, 4, 0, and 4, -1, 3, 13. And that's pretty much how you do all these types of problems. Let's see. Down here, these problems are similar, but I'm gonna put them in another video.